good afternoon. My name is Atarud Azizi Namini. I'm director of the IBT ABC UTC. Very warm welcome to more than 1,100 sites that have registered to listen to our monthly webinar. Today we are delighted to bring another topic titled In-Service Deck Replacement I-90 Columbia River Bridge Vantage. We are delighted to have with us Amy Leland, State Bridge Design Engineer with the Washington State DOT, and Anthony Mizumori, a Bridge Design Engineer with the Washington State DOT. We'll be moderating the question and answer period after the presentation. Just a couple of information before we start. The 2026 World Bridge Engineering Conference is right. Actually, before you know it, we are going to be December 1st, 2nd, 2026. The conference is going to be held in Hyatt Regency Hotel in Miami, Florida. Thank you to many state DOTs that have co-sponsored, and the conference is sponsored by U.S. Department of Transportation through our University Transportation Center. Call for abstract is out. You can go online and submit your abstract. There's also possibility of you can exhibit. I can tell you that the number of the exhibit that we have this year is a little bit limited, so please reserve your exhibit booth as soon as possible. We also have block of rooms at the conference rate. December, as you might guess, is a very popular time in Miami, Florida. So this is a special rate for the conference, so please take advantage of that. More importantly, we are delighted to let you know that the conference is going to include the award program. The Calvert Award nomination right now, it's going to be open through the June 30, 2026. The categories that we have for this conference is divided into the several categories. We have an Innovative Bridge Engineer of the Year. You can nominate who you think that it's an Innovative Bridge Engineer of the Year, and the Innovative Bridge Owner Agency of the Year. Also, we have awards in the project category, in two different project categories. One is a ABC project of category, and one in Innovative Bridge Technologies. For each one of them, we have three different levels: under $10 million, between $10 and $100 million, and more than $100 million. All the information how to nominate is on our website. You can go to our website and submit your nominations. So we hope that you will, if you have a good projects in mind, please go ahead and submit the nominations. And more than that, we hope that you will mark your calendar to attend the conference. So at this point, I'm going to turn it to Kathy, who's going to share with you some additional information. Kathy?
Thank you, Torad. My name is Kathy Kroll. I am a co-director of technology transfer at the IBT ABC UTC. I'm very happy to welcome so many attendees today. I know Torad mentioned that there are over 1,100 registrations. It's a really great, so good that we can reach out to so many people in the bridge community. So today we are on our 174th webinar, and we're happy to have you all here with us. The IBT ABC UTC is sponsored by the United States Department of Transportation through its University Transportation Program. We've had a number of questions from people how the UTC, what it is. So we're trying to explain better and really give credit where credit is due. So the University Transportation Center's program has been in existence since 1987, with a mandate to help address our nation's ever-growing need to maintain and enhance our transportation systems. So our UTC, the IBT ABC UTC at Florida International University, and our partner universities are focused on accelerated bridge construction and innovative bridge technologies. But we would very much like to express our appreciation to the US DOT and their UTC program for supporting the IBT ABC UTC so that we can continue to serve the bridge engineering community with things like this webinar. Before we get started with today's webinar, I'd like to share a few announcements. We will start with a few upcoming events from our industry partners. The AISC and SBA will be sponsoring Steel Days 2025. This is a national event to be held October 20th through the 24th that offers steel enthusiasts, both young and not so young, opportunities to learn about careers in the steel industry. See the link for additional information. The American Segmental Bridge Institute, ASBE, will be holding their 37th annual convention in Bellevue, Washington, October 27th through the 29th. See the link for additional information. The next slide is a different type of announcement. We intend to share one interesting current piece of information from the bridge engineering industry each month. This month, we highlight a recently published NCHRP synthesis document on bridge construction inspection training. This studied training programs across the country and assembled best practices by way of case studies from states with robust training programs. The states with case studies are California, Colorado, Georgia, Michigan, Minnesota, and Pennsylvania. So thank you to those states for sharing your experiences. This is a really valuable resource for those wishing to improve their bridge inspection training program, and it's available for no cost in electronic format at the link below. Now on to a few of our own IBT, ABC, UTC events. The first is actually an event that has passed, but we wanted to highlight the fact that the annual in-depth web training that was held on September 9th has been archived and is available for viewing. The topic was simple for dead load, continuous for live load steel bridge systems. You can find the archive on our IBT ABC UT website and see the link on the screen. Our next monthly webinar will be held on Thursday, October 23rd from 1 to 2:15 p.m. The Texas Department of Transportation will be discussing the topic of research and the implementation of that research in their bridge program. Robert Owens, the Bridge Design Section Director, will be presenting. Last announcement, our next quarterly research seminar will be held on October 31st from 1 to 2:15 Eastern. Our colleagues at University of Nevada, Reno will be presenting on data-driven computational framework for rapid post-event damage assessment of bridge infrastructure assets. Please mark your calendars and join us for those events. That's all for our announcements. On to our standard housekeeping items. As many of you know, these webinars are recorded and posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation is provided in the GoTo dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. With that, we will begin our feature presentation. I invite the presenters. We are happy to welcome Amy Leland and Anthony Mizumori from the Washington State DOT Bridges and Structures team. Thank you both for sharing your time and expertise with us today. With that, we'll turn the screen controls over to the presenters.
Well, welcome. Thank you all for coming today. I appreciate it. I'm Amy Leland, as Kathy mentioned, and I am the State Bridge Design Engineer for Washington State Department of Transportation. I'm here along with Anthony Mizumori, who's one of our senior design engineers and our concrete specialists. And we are here today to talk about this project, the Vantage River Bridge Deck Replacement Project. So a little bit about Washington. Let's introduce Washington State. For those of you who do not know, we are located in the northwest corner of the continental US, as you can see here in red. For Washington State DOT, ourselves, we tend to design approximately 50% of our designs in-house. I know different states do it differently, but in Washington State, that's approximately our percentage that we do ourselves. Another figure of Washington State, this one you can kind of see some topography. And what I want you to notice is that there is kind of a difference as you go from the west to the east part of the state. So here I drew in a little line and it kind of indicates the separation between west and eastern Washington. We have a lot more moisture on the west side, we have higher seismic on the west side, we have a lot more greener on the west side. On the east side, it tends to be drier, a little bit more, grassland and whatnot. So it's kind of, for those of us in Washington State, we tend to say we're from Western Washington or Eastern Washington. So here, going more in depth in what we have, on the west side, we have rainforest. You can see a picture here. We have a lot of moss on the trees. It's just a beautiful arena. Then we have our mountains. We have a lot of mountains in our mountain ranges. This one is our most famous mountain, is Mount Rainier. It's over 14,000 feet in elevation. You can see just the greenery we have and the trees, they look fairly small in relation to that mountain. On the east side of the state, then we have a little bit drier arena. We have more farmlands, and we also have a lot of apple orchards. Washington is known for its apples. Now let's get to the heart of this. We have bridges. So in Washington state, there are approximately 7,700 bridges, and those are state-owned and local agency structures. So 3,412 are owned by Washington State DOT. Our structures, we have 8.5% are in poor condition as of fiscal year 24. The average age is 51 years. We have 315 bridges older than 80 years. I do want to point out that the bridge we are talking about is not in poor condition, it is in fair condition. Now let's talk about our bridge decks. So we have 72 of our bridges are due for rehabilitation, and that means that between 2 and 5% of the deck area is patched or spalled. We have 59 of our bridges past due, more than 5%, and 23 in contract for rehabilitation. On the map to the right, you can see our main state routes, our corridors. So going from north to south is I-5, and that extends all the way down into California. Going east-west, we have I-90, and I-90 starts in Seattle and goes all the way to the East Coast. The Vantage structure that we're talking about today is near the middle of the state on our I-90 corridor, so it has a lot of traffic. Now I'm going to turn it over to Anthony so that he can talk about the main specifics on this particular project. Thank you.
All right, thanks, Kathy. Thanks, Amy. So I will get into the details of this deck replacement project, which is currently under construction. Here you can see the Columbia River Bridge at Vantage with a 520-foot tight arch main span and several plate girder approach spans off the side of this slide. So what I'm going to cover today is some of the history of the site and the bridge, as well as the existing conditions on the bridge deck. I'll talk about some of our project goals, and then go through several of the structural solutions that we developed along with construction photos. So the bridge location is circled here in the center of the state on I-90, as Amy mentioned. High ADT, very high truck percentages, and the two shortest detours at this location are both over 100 miles long. So it was not a good candidate for any sort of extended closure to lanes or the bridge entirely. Here are a couple photos from the first crossing at the site. In 1914, a ferry was put into service. It carried 2 cars, and it was quite dangerous. They learned quickly that you had to chain the wheels down to the deck in order to keep them on the ferry. 3 years later, in 1917, Washington State took over and operated this ferry. So it was the first state ferry in Washington, and today Washington State owns and operates one of the largest ferry systems in the country. This photo here shows the first bridge constructed at the site in 1927. It's a 2-lane bridge, 1,600-foot cantilever truss, and it was the 7th crossing over the Columbia River. In 1959, the Wanapum Dam was constructed downstream. There were several dams constructed along the Columbia in this era, and the waters behind this dam were planned to inundate the road and original bridge at the site. These photos here show some of the flooding of the area behind the dam, and you can see the existing route being inundated. The new bridge is under construction downstream, shown here in 1962. So you can see the tight arch span being constructed using the cantilever construction method. And the photo on the right shows some of the deck construction work on the cast in place deck. And here's a photo of the bridge shortly after it was completed. This completed the east-west route on I-90 throughout the state during the interstate period. This bridge is 2,500 feet long, and it contains rivets, bolts, and welds. It was constructed in this era where all 3 were in use in the industry. So jumping ahead 60 years, here's some photos of what had become pretty typical maintenance crew work to patch and repair the bridge deck. It wasn't uncommon to see the Columbia River below your feet out at the site. And you'll notice the PPE on the crews on the right. That was because this work was done during the pandemic era. It's not tied to the particular materials that they're using. So some of the key project challenges that we needed to address, one was, given the span lengths, structure deflections under traffic provided a lot of constraints to our design and construction methods. Weather is also a concern here. We have high temperatures in the summer and cold, unworkable temperatures in the winter. And everywhere along the Columbia River Gorge, wind is an issue that could potentially shut down construction activities. We also had ongoing bridge deck maintenance that needed to be performed alongside the deck replacement work. And this bridge also is an emergency service route for communities on either side of the bridge. So again, a full closure of the bridge was not a very viable option. And then lastly, given the construction delays predicted for this project, which were up in the 4-hour range at peak demands, there's an extensive effort to communicate traffic delays and impacts to motorists many miles away from this bridge so that they could properly plan their detours if needed. So the scope of this project specifically is to replace the existing cast-in-place concrete bridge deck with a precast concrete bridge deck. And one of the requirements was that we maintain the current load rating to allow the overload freight to continue to use this bridge. And we largely achieved that by constructing a bridge deck that was slightly lighter than the current bridge deck. Traffic staging was a big part of the challenge for this job. We were committed to maintaining one lane of traffic in each direction at all times throughout the deck replacement work. And additionally, we needed to open the bridge to full traffic on 3 key holiday weekends during the summer and during the extended winter work shutdown. So this project was awarded in January of last year to Garco Construction for $57 million, and we're expected to be finished in mid to late 27. So looking into the structure details a little, this section here is in the truss and arch spans. It's a pretty typical framed floor system structure with 7 stringer lines. And the section on the bottom shows the steel plate girder approach spans. These plate girders are spaced at 16.5 feet on center. And when you combine that with the need to run a construction joint down the middle of the bridge, we had a lot of challenges supporting traffic and construction loading on without overloading the existing deck. And I do want to point out that the existing deck is non-composite with the stringers and girders, and we oftentimes like to consider making deck replacements composite in order to boost the live load capacity. But we did opt to construct a non-composite deck in this case, given the complicated staging of the job, which I'll go through. So here's a schematic drawing of the precast deck panel concept that we used. The deck panels span half the bridge width with the longitudinal joint, and the exact length of the panels was left up to the contractor so that they could balance their means and methods with the construction equipment loads imposed on this job. These panels are joined with ultra-high performance concrete closures running transversely and longitudinally. And you'll note there's no pockets in these panels for shear connectors because, again, the vinyl deck system is non-composite with the supporting structure. So I'm going to step through the construction sequence for the work in plan view here. I'm going to run through the contractor's actual sequence. And it might not all make perfect sense, but I do want to highlight how we're proceeding with the work symmetrically from the left and right lanes of the bridge. And that requires a lot of traffic shifts. So the first 2 work zones are shown here in blue, where we're replacing deck panels, and traffic is staged to the opposite side of the bridge. These 2 work zones are worked independently and accessed from opposite ends of the bridge. Once the deck work is done in this zone, we flip traffic and work on the adjacent portion of the bridge deck. And once those are in place, we connect them down the center line of the bridge with UHPC. From there, we continue on working the deck in a symmetric fashion from left to right. And I do want to point out, pausing here, you'll note that the length of these work areas only encompasses about half of the span for the steel plate girders. And that's because the bridge deck is a big part of the transverse load distribution system for live load, as well as construction equipment. And we weren't able to have a longitudinal joint run the full length of the span without overloading the existing cross frames. So I'll step quickly here through the rest of the sequence. You can get a sense of the number of traffic shifts required to accommodate the work in this fashion. And now if we look at a section view of the deck in one of these work zones, shown here is the existing condition where we have 4 lanes, 12 foot wide, 2 in each direction. The first step is to restripe the bridge with 10.5 foot lanes and slide those to the curb line as close as possible. Once that's done, We install a temporary steel floor system down the center bay between the girders here to support the deck after saw cutting starts. Once this floor system is in place, we can shift traffic to one half of the bridge. So we have two 10.5-foot lanes of opposing traffic, undivided, and we can start removing portions of the deck on the right side, bringing in precast deck panels, which are also supported on a temporary floor system in the center bay. So the haunches are grouted between the deck panels and beams, and UHPC closure pours are cast between these deck panels. Then we can move traffic to that side of the bridge, the right side, and commence with this similar work on the right side to remove the deck panels, place a new deck, and then cast haunches and closure pours. Once this work has gained strength, we move to our third traffic configuration where we split lanes to provide a center work zone. And this provides access to cast a longitudinal closure pour using ultra-high performance concrete down the middle. Once that gains strength, we have the option to open the bridge up to 4 lanes of traffic if required by the contract, or we can move on to the next work zone. And it's at this point where the temporary floor system in the center bay could be removed by the contractor. So I want to talk a little bit about analysis for this project. Here's our model for the plate girder approach spans, and I'm going to focus on that in the presentation because some of the bigger challenges were in the approach spans rather than the main span. So the analysis for the finish condition was pretty trivial because we were reducing the weight of the deck overall. But we had a pretty extensive analysis for construction load configurations in order to identify the sequence required in the plans, as well as construction equipment load limitations in the plans. And it turns out that the cross frames, as mentioned, were some of the more vulnerable elements that needed to be addressed during these temporary conditions when the deck was in a state of partial replacement. So getting into construction, this photo here shows a typical deck panel being hoisted from its forms. It's a 30 kip panel, and the contractor elected to cast these in 7.5-foot lengths. The thickness ranges from 8 to 10 inches. Concrete is 5,000 PSI. And in the approach spans, we used grade 80 reinforcement, and that provided a reasonable bar spacing in the UHPC closures to provide reasonable fit up as well as efficient non-contact lap splices between the bars. You'll notice that the bar is galvanized as well. We had specified epoxy coated bar in the contract, but the contractor proposed a no-cost change to use continuously galvanized bar on this job, which we accepted. So this is actually the first significant use of continuously galvanized bar for WashDOT. Looking at the deck panel finishes, the 2 images shown here are mock-ups for the roughness provided, one by a wire brush and one by a broom. The final bridge deck will be ground and grooved to provide skid resistance, but some of the initial deck panels on this job will be in service for up to 3 years. So we needed skid resistance, and we opted for a wire brush finish shown on the top there. And this mock-up panel was used as the basis for acceptance of the production deck panels. Additional photos here show the exposed aggregate surface finish for the UHPC closure joints, and the bottom right shows a form liner finish which we applied to the soffits of the deck panels over girders and stringers to provide some mechanical roughness to promote bond, even though the deck is non-composite. Getting out on site here, these photos show the work access that the contractor installed to install structural steel floor system elements, as well as form and strip for the haunches and UHPC closures. We provided a 10 PSF allowance under contract for this work access system, and the contractor was able or allowed to install this in any permutation they wanted to perform the work, including the full length of the structure. Now onto cross frames. So the original cross frames were just sized as secondary members. So they had a risk of being overloaded during construction. And the photo on the left shows a typical strengthening that we did where we replaced the riveted connections with high strength bolts. That was done on most of the cross frames on this bridge. The photo on the right shows more extensive strengthening down the center bay at key cross frames, where we converted single angle members to symmetric double angle members. This photo here shows the temporary steel floor system in the center bay of the girder spans. So the stringers run left to right, and they support the cantilevered edges of new and existing deck panels when they're unsupported. And these stringers are supported on transverse floor beams, which are bolted directly to the existing transverse stiffeners of the girders. And it's this floor system which allowed us to support 2 lanes of traffic as well as significant construction loads on the bridge at the same time. This photo here shows temporary top flange bracing in place. This resists lateral torsional buckling while the deck is in the process of being replaced. Although the deck is non-composite, it does provide continuous lateral bracing to the compression flanges in the positive moment region. And as we start to saw cut out panels of the existing deck and set new deck panels down, we lose that stability. So these transverse braces provide lateral torsional buckling resistance. And typically a transverse strut alone is not sufficient to resist lateral torsional buckling, but because during this work, we always have at least 2 of the 4 girders fully braced by a deck panel, whether it's new or existing. So these simple braces function as a lean-on bracing to provide resistance against buckling for the system of girders. They're much more economical than a full cross-frame installation. Getting to the top of the deck, this shows some of the saw cutting work that was done first to remove the barrier and a portion of the overhang, and then larger portions of the existing deck could be removed. And the wood decking in the foreground here is actually access provided over a gap where a portion of the existing bridge deck had been removed. And this photo here shows a half-width section of the existing deck being picked out of place and loaded onto a flatbed truck using this large gantry system that was used to perform the work. You'll see the 2 existing girders in place, as well as some of the temporary stringers on the lower right side of this view. And a little bit about deck panel removal. So the original deck was non-composite, so no shear studs. And so the plan was to pick out portions of the deck in fairly large segments as shown in the previous slide. However, during some of the early work, the contractor was finding that these panels couldn't be picked. So they had to do a fair amount of chipping over girder flanges to free them and cut the deck panel into much smaller segments. So this initially seemed to jeopardize the project schedule as a whole. But what we discovered was that this restraint was not coming from shear studs, but you see in these photos, there's deck soffit form hangers that straddle the beams. And it turns out that some of these were occasionally tack welded into place during initial construction. Once we figured that out, the contractor was able to come up with a way to locally jack at points of restraint when they're lifting deck points and pop the tack welds with a very low level of force. And this allowed us to maintain the schedule and plan to lift out deck panels in pretty large sections. So this photo here shows the gantry system lowering a new deck panel into place. So this work occurs sort of in reverse to removal of the panels, where a flatbed truck backs up underneath this gantry. A moving crane picks, rotates, and translates the new deck panel into place where it can be set down onto leveling screws that are supported on the underlying girders, as well as temporary steel floor system. So this gantry was custom built for the job, and in fact there was 2 of them because we have 2 independent work zones operating at any given time. And the weight of the gantry, the flatbed truck, and a panel in transit was right around the construction equipment load limit that we had developed and put in the plan, so that they took full advantage of that allowance. You'll also see here that this gantry has telescoping members transversely at the ends, and that's so the width of the gantry could be adjusted. So when they're mobilizing this gantry on and off the bridge, it's in a narrower configuration to fit within the lane. And when it's operating on the bridge deck, this adjustment allows the solid rubber tires to be located directly on top of existing girders or stringers, depending on which span they're working in. So this avoided inducing large bending forces into the new deck panels when it's traveling over new deck panels. So there was no need to provide any sort of pre-stressing in these panels for temporary load configurations. This photo here shows the gantry system being mobilized at a bridge end. When it's operating, the gantry supported on solid rubber tires that are shown installed here, but the photo on the bottom left shows the rubber tire system that was swapped in and out when they're mobilizing the gantry up and down the approach roadways. So a little bit more about construction load limits, because we did all the construction engineering globally during design, and the diagram here shows the construction equipment load that was put into the plans. It's a 2-axle, 2-wheel line load at 100 kips total. And the contractor was allowed to use any configuration of equipment as long as the load effects created an envelope less than this notional load that we provided. In addition to that, we had some requirements that only one panel be removed at a time to avoid unbalanced dead load configuration. And we did allow them to work 2 separate work zones as long as all the equipment was separated by at least 225 feet to avoid excessive interaction between the load effects. And as I mentioned earlier, they were allowed an additional 10 PSF of load for access below. So this photo here shows panels in place just after they've been grouted. Grout is placed through holes in the panels themselves, and the detail on the left shows a simple haunch detail for that grout placement. Bottom left shows some performance requirements for the grout so that we were assured that we had a durable material, because this grout will be present at the deck surface. And I won't go into the durability requirements, but they're there to review later if you're interested. Once the panels have been grouted above the beams, the UHPC closures are made in the transverse joints. So this photo here shows mixing of the prepackaged proprietary UHPC provided by CNTech. We are anticipating about 320 cubic yards of UHPC total on this job, and so far this work has gone fairly well. This is the 3rd unique supplier of a prepackaged product we've used on state work. Here are a couple photos of the UHPC placement into the transverse closures. Note the photo on the right that the transverse closure is integral into the raised concrete curb as well, and that detail was pretty helpful here because it allows fluid head to be maintained on the UHPC while it's in a flowable or plastic state. And if there is any settlement that occurs or leakage while it's in a fluid state, the low points tend to show up in the curb rather than the roadway section itself. This photo here shows forms in place while the UHPC is gaining strength. So the UHPC had a 28-day strength of over 20 KSI, but we were targeting 14 KSI to be able to load these deck panels with either construction equipment loads or traffic live loads. And they were able to achieve this in about a day or a day and a half typically. A little bit about the haunch details on this job. So this half section here shows the existing haunch as well as the new haunch on the right. The existing haunch is monolithic with the deck itself, and it encases the top flange laterally, and that's what provides reliable compression flange bracing in your positive moment regions. The detail on the right has a simpler square-edged haunch, and there is some surface roughness or interface shear transfer across these joints. You know, we roughen the soffit of the panels, and the girder flanges often are have cover plates that are riveted in place. So there's a lot of mechanical roughness to provide interface shear transfer that could arguably provide lateral bracing to compression flanges. But we wanted to provide some additional measures. So the photo on the right, you can see the darkened transverse UHPC closure, and where that intersects the girder flange, we actually constructed a filleted haunch area here to provide some additional lateral bracing to that girder top flange. And this photo here shows the 3rd traffic configuration where we had split lanes to provide the central work zone. So we've got 2 lanes operating on the ends of the bridge, and they're getting ready to mix UHPC here. One of the big concerns for this work was vibration that could deteriorate the UHPC joints while they are gaining strength. And the measures that we took were to move the live load as far from this joint as possible. We also reduced speed from 60 miles an hour to 40 miles throughout the job. And we did require that the form systems provide resistance against relative movement in the 2 panel edges. A little bit about expansion joints. So this bridge contained 3 large steel finger joints to accommodate most of the movement, and we opted to keep those finger joints in place. The photo on the right shows a finger system that had been pulled out and offsite where they can make repairs to the existing system, even though it was generally in a pretty good condition. And this was reinstalled on the on the deck. The photo on the left shows it in place. We did have to extend the finger joint system slightly to account for the new curb system. And we did have to shim these finger joints up a little bit higher than they were originally sitting because the new deck panels sit higher than the existing deck. And we had to do that to provide enough space to reliably cast the girder haunch grout underneath the deck panels. This graphic here shows how we addressed the grade difference at joints between the existing deck and the new deck. The new deck is shown on the right. So we have a bolted steel plate that spans the 6-inch gap and protects the extended rebar from the new deck panel. And then there's a pavement wedge to ramp up to this plate on the existing deck. These photos here show that transition plate in place from above and below. The photo on the right, you can see some temporary steel edge beams in place as well. And these edge beams were necessary to support the free edge of the deck panels at these transition locations. And they also stiffen the system, which was helpful because these through bolts that held the plate in place through the existing deck were somewhat fatigue prone given the flexibility of the deck. It was a little tricky to make sure we had adequate tension to hold the plate in place and avoid any sort of fatigue failures. So these panel edge beams help reduce that deflection and vibration as well. I want to talk a little bit about contingencies that we ran into. Any deck replacement job, you're bound to find some surprises once the concrete is removed. These photos here show one of the worst conditions we encountered. This is a transverse floor beam in the arch spans where you can see the cover plate has experienced section loss, pack rust between the plies, and that has removed or popped off many of the rivet heads that connected the two cover plates. We weren't able to remove and replace this plate in kind because it's still carrying load because there's traffic on the opposite half of the bridge and there's deck dead load in place. So we opted to install a second cover plate over the top of this and replace the rivets with high strength bolts. This plate only ran half the length of the floor beam because that's all we had access to. And then when we moved to the other half of the bridge, we installed a similar cover plate and connected those two cover plates using a partial joint penetration weld out at the mid-span of the floor beam itself. And so far, the rest of the floor beams and the girders were generally in good condition, and oftentimes the red lead primer paint was fully intact. Another contingency that's pretty common on deck replacement work is errant saw cut damage here. Photo on the right shows the worst case that we encountered, but unfortunately this occurred in the plate girder spans near a pier where there's high tension load demand in these plates. And they misjudged the cut depth because of the stack height of these 3 cover plates present on the girder at this location. Our typical repair is just to perform a slot weld to reconnect across the cut. This cut was actually a little trickier because you can see it penetrates down into that second ply. So we did repair it with the slot weld, but one of the concerns is by bridging the 2 cover plates that are otherwise only connected by rivets, we're creating a potential fatigue risk there. So our solution was to come in from the side with a cutting wheel to make a curve cut to sever the slot weld between the 2 plates and hopefully improve the fatigue performance of this repair. Some of the lessons learned that I can share. One is that UHPC can be placed and cured when exposed to modest vibration. This was again one of the biggest risks going into the site because most of the literature will tell you to not to expose the UHPC to any vibration. But the suppliers will acknowledge that this material has been placed when there is vibration present. We did our best to limit the vibration in these joints given the traffic requirements for the bridge. 2, large construction load allowances can be combined with active traffic as long as responsibilities are clearly specified and adequate time is given during the bid period. So we did a fair amount of construction engineering, but in order for the bidders to provide an economical bid, they needed time to run some bid level construction engineering of their own to size the equipment and schedule out the work. We did delay the bid period once for that reason, but we also were the benefit of some additional bid opening delays tied to administrative issues with the state and the project budget. And so I think that was key towards getting economical bids. And there were some bids that were quite a bit higher than the low bidder, and I suspect it's likely because they weren't able to perform enough bid level engineering analysis to optimize their schedule. And lastly, non-composite precast reinforced concrete panels are a viable deck replacement option. And that's not something that WashDOT has done regularly. There's not a lot of literature out there for that. And it'd only be recommended if you're replacing a deck that is already non-composite. And with that, I'll open it up to any questions.
All right, thank you. Thank you for very informative presentation. At this point, we are going to turn it to Paul and Bijan to moderate the question and answer period. The question and answer period could run to about 15 minutes after the hour. And if you do not get the time to answer all the questions, the answer will be provided on our website later. Paul?
Okay, Ataru, thank you. Anthony, all right. Good job. We do have a whole lot of questions, so we'll go ahead and dig in. It's 1:50 now, so we'll see what we can do. We had some questions that came in beforehand. The first one here is, were stainless steel rebars, they weren't used in the replacement, were they considered at all?
WashDOT doesn't have a lot of experience with stainless, and our epoxy coated bar has held up generally well, so we didn't see the need for that. We've used it in cases with lightweight concrete and FRP reinforced decks selectively, particularly for bent bars, but it's not common practice in Washington State.
Okay, then another question came in beforehand. Did you do any foundation analysis for the existing bridge with what your construction changes were?
We did not, and because the existing bridge deck is slightly lighter than the existing deck, we didn't feel that was necessary. We did do some strengthening of the piers and minor repair work to improve the load rating capacity to avoid any substructure issues, but not specifically for the foundations.
Okay. What was the contractor's learning curve for the precast decks? Did he get going faster after he got a few of them under his belt?
Yeah, there definitely was a learning curve. It's hard to identify the specifics timing because I alluded to or mentioned that some of the initial panels required some chipping until we got a handle on addressing the form tie or the form hangers. But they were probably, for a work zone in the approach bands, they were probably in the 3 to 4 week range to perform a work zone, and now they're in sort of a 2.5 week time period to perform that work now, and it's become pretty routine. It's they describe it as wash, rinse, repeat at that point. We're about 40% of the way done with the deck replacement work.
Okay, do you feel that the precast decks save time? I think that probably occurred.
Yeah, I think cast in place wasn't really viable given all the vibrations there, so we never really developed a schedule for that. I don't know that. I think the access constraints are the bigger schedule impact than the use of precast itself in this case. But for a new structure, I think there certainly would be some speed benefit to a precast deck.
What about saving money? How do you feel on that?
Yeah, it's hard to provide an apples to apples comparison. Handful of projects that I've seen where an alternate was proposed, the cost differences weren't drastic. A similar bridge further downstream on the Columbia River that I worked with, contractor proposed a switch from cast in place to precast. It was actually a slight cost increase, but they were proposing to save some time, but we didn't elect to accept that proposal on that structure.
Okay. What are the primary differences between UHBC pour strips and conventional concrete cast in place pour strip?
Well, the size is the big one, and given our limited roadway width, we couldn't have accommodated a conventional closure pour down the center of the bridge and still had room for traffic lanes and barrier connections. So the UHPC was really the only thing that worked geometrically on this project. And I think The rapid strength gain was also important to minimize the risk of any vibrations or deflections from overloads that a conventional concrete would have been more prone to.
Okay. Have you noticed if precast deck panels work better on steel girders versus concrete girders?
I can't really speak to that. We don't have a lot of precast decks in the state to address that.
Okay. We had a question here about live load vibrations. Were they considered for the UHPC closure forecasting?
Yeah, that was definitely one of our main concerns, and so we sort of took every best practice we could to minimize those vibrations, but acknowledge that they still did exist. And these steel bridges, you can definitely feel the vibrations, especially when there's trucks crossing the bridge. But I think the steel floor system stiffened things up as well, so it's really the relative deflection and vibration that you're looking to minimize. And that was pretty modest. And the contractor actually felt that in the end that our approach was maybe too conservative to eliminate vibrations, which I disagree with, but it was comforting to know that their comfort level was there given what they're experiencing on a daily basis.
Okay, but regarding that, was there any concern about the rebar development length with the vibration problem?
Well, that was sort of the underlying concern, is if you have voids around the bar, and that which would degrade the development length. We did provide some additional development length there out of an abundance of caution, but I think from everything we've seen, looking at these joints, while they're plastic and then after the fact, there's really no sign of any sort of deterioration or compromise due to vibrations.
Okay. The question came in beforehand about, was there any de-icing chemicals and pre-thaw cycles affecting the performance of the ABC connections over time? You probably haven't had it in that long, have you?
Yeah, not for this project. We do have a couple others adjacent deck girder bridges joined with the UHPC closures. We tend to provide an overlay over those, so that will help eliminate, environmental degradation. But for the UHPC itself, don't really expect that to be the weak point in any sort of environmental degradation modes.
Okay, we had a few questions on cost. What is the cost of the UHPC compared to conventional concrete?
Yeah, I don't know that I would call that an apples to apples comparison. What I can say is that the bid we received for UHPC was $8,000 a yard, and that's actually slightly lower than what we have seen on smaller volume projects, where it was more, it was around $9,500 a cubic yard. We've heard that the material costs themselves are around $2,500 to $3,000 a yard for this, but I would say that cost comparisons by volume, it'd be more appropriate to compare that to like a prepackaged grout or a non-shrink grout rather than concrete itself for field work like this.
Okay. Can you say what UHPC you use, and was it did the contractor put it in, or did you have a subcontractor do it?
It was CNTech was the product, and we had manufacturer representatives on site overseeing the work. The work was performed by our contractor, and we've actually been able to get some of the contractors' key personnel trained up by the supplier's representatives, so that we've relaxed our requirement to have UHPC material supplier reps on site for all of the UHPC pours. And so far that's gone pretty well. The contractor's personnel has been able to identify, issues in flow or consistency, depending on different temperatures, and they've been able to identify if there's any sort of mistakes in the batching of the product. So far that's gone well for us.
Okay, and then is there any appropriate cost, or could you identify any cost regarding the temporary support framing that was needed? Was that ever quantized?
So we have a lump sum bid item for that, and the reason is that the contractor is ultimately responsible for the total quantity of that temporary support steel. They only need it in place over the portion of the deck that they're actively working on. So there's a lot of ability to remove and reuse that steel. The lump sum bid item for our contractor was just over $2 million. And that's sort of in line with the lower end of what we were seeing from all the other bidders.
Okay. Then the person, and that was $2 million in what year?
24, January
Okay,
of 24.
24. Okay. Because somebody asked a question about what would it be in 2026 dollars. So we're not even there yet.
Yeah, can't say.
Maybe FY 26. Okay.
Right, yeah, and I'm sure the contractor, given that this job occurs over multiple seasons, I'm sure they factored some sort of escalation in there for inflation as well.
We had a bunch of questions about the non-composite nature of the bridge. And the first one, it said, why is the deck in UHPC non-composite with the girders? I think you kind of mentioned or explained that, I guess. I don't know if you want to elaborate on that any.
Yeah, I mean, per code, shear connectors and shear studs would be required to rely on that composite behavior at the strength limit state, and we don't have that. I think in practice, it's sort of assumed that there is some sort of composite action that occurs, and that's generally considered to be beneficial, but not relied upon.
Okay, there was a comment that test data shows that even non-composite beams act as composite until the bottom flange of the steel girder reaches yield point. Did you consider this, and would it make any difference?
We did consider that behavior. We were intending to rely on as much of that as possible to control deflections. Obviously, you don't know that going in during design, but we also did require them to grout and cast UHPC closures as they progressed to help establish any of this incidental composite behavior that could be useful to limit vibrations and deflections.
You sort of took it like, if we get it, that's great, but we're not going to put it in the design.
Right. Okay. Yeah. We didn't rely on any sort of quantifiable.
Okay. All right. And another question along that line was, how were the UHPC pores disconnected from the steel girders? I don't think you made any special effort to disconnect it.
No.
Were there any challenges with potential deflection differences between the two stages if they don't line up?
Well, I think a lot of that comes to leveling of the panels. We had adjustable leveling bolts, and there was some allowance for shimming. There's not a lot of dead load deflection in play here, so it can be fairly well controlled just with alignment. And the gantry system that they used had a lot of control mechanisms to really place these panels to a pretty high tolerance.
Okay. You didn't put any overlay at the end of the bridge. I mean, once you were done with it, you didn't go back at the end. Are you gonna go back at the end and put an overlay on it?
No, we won't. We considered that, but our plan is we cast a sacrificial grinding thickness into this. So we're gonna do a 1/4 inch grind with a plus or minus 1/4 inch tolerance to smooth out the ride. And then we'll do some longitudinal diamond grinding to provide skid resistance. And that'll leave us with 2.5 inches of cover. 1/2 inch of that is sacrificial. The reason we went with the full thickness panels there was to limit or to better handle bending stresses during handling of the panels. So we were able to use that thickness in the interim rather than applying a non-structural overlay after the fact.
Okay. How did the design and construction team handle the girder deflections and diaphragm connections during the deck removal?
I don't know that was really explicitly an issue. I mean, a big part of the work was to strengthen the cross frames ahead of time for the anticipated loads. But once that work was done, there was really no additional effort or concern. Okay,
now you didn't free up the cross frames in the center bay, did you, to disconnect the two sides?
No, we didn't. On a much wider bridge, I think that would have been a viable option, but because of the wide girder spacing and the need to have 2 lanes of traffic, that steel floor system was required to support the deck panels. So it would have sort of been in conflict with the freeing up of the deck panels themselves. Or I'm sorry, freeing up of the cross frames themselves.
Okay, next one I have here is, What was the benefit of using the galvanized bars rather than epoxy coated bars?
Yeah, there's a lot of opinions on that. I think our state policies are, right now is that from a long-term corrosion perspective, they're essentially equivalent. So designers have the option. There's a cost difference generally, but again, in this particular case, the proposal from the contractor was for a no-cost change. So we assumed that that meant that there was a slight benefit to the contractor, and because it was really no difference to us as a state, and it provided an opportunity for us to get some experience with this bar, we saw that as a benefit. There were some lead time issues with the continuously galvanized bar. We did actually replace some of the deck panels with the epoxy coated bar until the supply could get lined up for the continuously galvanized bar.
Okay, there was a question. What were the dimensions of the joints which were poured with UHPC? How wide were those?
The center joint was 9 inches with a 7-inch lap splice, I believe, and that is a splice on the primary flexural bars in the deck. I think it was a little narrower in the main spans because that closure occurred over a stringer that's much more tightly spaced, and they were 6-inch joints transversely.
Okay, and then the question was in the lap splices. Those were non-contact splices, weren't they?
They were non-contact splices, so yeah, the bars projected from the panels at a 6-inch spacing, and so there was a 3-inch stagger between the bars across those joints.
Okay. How many years do you expect to get out of the bridge in service now that when you get it done? What are y'all looking at?
Yeah, I mean, we'd hope for over 50. 75 would be great. I don't know that we have a lot of data to point to that, but I mean, obviously, precast concrete, it's a pretty durable material, no shrinkage cracking present, and the UHPC itself should outlast anything else on the bridge, most likely.
Okay, when was the original bridge built?
1962.
62, okay. And now it's 20, okay. And what was the cover on the original bridge? 2 inches?
Yeah, I'm assuming it was 1.5 inches, possibly 2. There was an overlay installed on the bridge, 1.5 inches modified concrete overlay as well, but that was much later.
Okay. Did you replace the barriers on the bridge? What'd you use for new barriers?
Yeah, so the existing bridge had a concrete parapet that had been retrofitted with a Thri-beam rail, and the new system, we had a concrete curb which was integral to the deck panels, and we used an Oregon 3-tube railing system. So it's a metal rail, and that allowed for easier connection between deck panels. And it's also a lighter weight system, so that helped us balance the load rating concerns and ultimately allowed a lighter weight system than the existing deck.
Okay, what is the total construction duration? What did you estimate going in? Total contract time?
Let's see, yeah, we awarded in January of 24, and I think we were planning to be finished in, say, the first half of 27. And I think that schedule has been extended now to sort of mid to late 2027. Okay. Yeah, so a little longer than we had initially anticipated. Okay. And part of that came from this need to open the bridge deck at 3 key weekends during the summer. And that actually takes a lot of usable time out of the schedule, because if the contractor can't complete a work zone between those calendar dates, then a larger period of time actually becomes unworkable.
Okay, can he work in the winter, middle of the winter?
It's generally too cold to place grout and UHPC. So contractor for this season, the contractor is probably going to work through late October, and we'll shut down for winter and probably open back up early spring, similar to the last year.
That's the east side of the mountains, I guess.
Yep. Yep.
Okay, it's 10 after. I'm going to go ahead and get Bijan to come in and help me here. We still have a lot of questions still coming in. Bijan, you there?
Yeah, I'm there. Thank you, Anthony, for a great presentation, and Amy. So we have, I believe, probably about 40, 50 questions. So we don't have obviously time to go through that. I can bring some of those up for you. So first question, why is the deck and UHPC non-composite with the girder?
I think, yeah, similar to previous question, we didn't have any sort of shear studs or shear connectors on those. And so per code, you would need that. You need to design those for strength and fatigue, which we did not. So yeah, we do anticipate that there is some composite behavior that exists because there is a fair amount of profile on the top of those girders with riveted cover plates, but the calculations does not rely on that composite behavior.
Okay, good answer. The second question, how is UHPC purse disconnected from the steel girder?
Oh, I think that was one that Paul had too. Yeah, we didn't disconnect that at all. You know, there could be some engagement in those closures, again at the rivet heads, but yeah, no measures taken.
Okay, next question. Are there any challenges with potential elevation differences between the two stages if they don't line up?
Oh, these are kind of sounding like Paul's questions. I think that one I did answer.
What are the size of precast panels compared to the bridge widths? How many panels through the width of the bridge?
Each panel was half the bridge width, so they were about 30 feet long.
And how many panels? Good.
Yeah.
No worries. You get these questions, you know, as to answer.
Yeah, I mean, we're probably around 650 panels total, and close to that many shop drawings, unfortunately.
What is the base grade 80 reinforcing bars before the continuous galvanizing A61 or A706?
Oh, I see. Yeah, it's an A706. We use A706 exclusively for wash dot work. There's really no cost difference for us, and most rebar is dual certified anyways. So we get all the weldability benefits if needed, which we don't take advantage of very often. But
the width of the PC deck panel varies depending on the contractor preference. The width of the PC deck panel could affect the UHPC quantity. How was this handled on the engineering estimate and the actual UHPC quantities after the bid?
Yeah, that's very true. I think we tried to capture that reasonably with the quantities we estimated. I think the contractor chose panel sizes that were on the smaller end of the spectrum, so that our effective costs will be higher than the bid costs because of the overrun based on their choice.
Next question, what material was used to transition that ramp?
Yeah, so this would be the ramp at the transition between new panels and existing deck. We're using an HMA wedge right now, and those have held up pretty well. But we had specified in the plans a cementitious-based material there because we assumed that would have better bond when cast in a very shallow wedge. It turned out that controlling cracking and bond was actually harder with cementitious material. Given the flexibility of the deck, yeah, those didn't hold up well. So we moved to an HMA.
The last question I thought, what is the total construction duration estimated?
Yeah, we're looking to finish up in mid to late 27, and we started. It was awarded in January of 24. Work started in the early summer of 24, and that was mostly deck repair work and structural steel installation. The deck panel work didn't start until maybe August of 2024.
Great, Anthony. You have many more questions. I think you will get it to answer later. I pass it to Kathy and Arturo. Thank you very much.
Okay, thank you. Thank you, Bijan. Thank you, Anthony, for a great presentation, and thanks to Amy also. And on that note, we are going to conclude our September monthly webinar and hope to have everyone back with us for October. But again, please don't forget to put the 2026 World Bridge Engineering Conference on your calendar, December 1st and 2nd, 2026. And please consider nominating Innovative Bridge Engineer of the Year, Innovative Bridge Owner Agency of the Year, and the projects in different categories that we are going to have an award. So all the information relating to the sending your nomination for the awards on our website. Please visit our website to fill the forms and submit your nomination by the deadline. On that note, we are going to conclude our webinar and hope to have you back with us in our next event. Thank you.